GATE 2014 Set 3 EC question number 32. In the circuit shown in the figure, the angular frequency omega in radians per second at which the Norton equivalence impedance as seen from terminals B, B' is purely resistive is being asked. For NPTEL reference, you can refer to lecture number 53, Norton's theorem of the NPTEL course, Network Analysis by Professor Taposh Kumar Bhattacharya, Department of Electrical Engineering, IIT Kharagpur, and the YouTube link is given here. For useful data, you need to know that Norton's theorem can linearize a circuit. Norton's theorem can simplify a linear circuit across two nodes with a simple current source connected in parallel with its equivalent impedance and in parallel with the two nodes across which the load is connected. So if you have a complex circuit like this and then you have two nodes A and B across which the load is connected, then the whole all over circuit can be simplified with an equivalent circuit which has a Norton current source in parallel with the equivalent impedance of this complex circuit in parallel with the two nodes. To find the value of the Norton impedance, which is the equivalent impedance, you remove the load, and from these two nodes you need to determine the equivalent impedance by deactivating all the active sources which are independent in nature, and then the voltage sources should be shorted, that is replaced by their internal impedance which is 0, and then the current sources should be open circuited. If dependent sources exist, then you need to deploy some test voltage source which is 1 volt taken and which is known in nature, and then fit it by removing the load across these two nodes and determine the current, then divide V test by I test, which will give you the Zn, that is the Norton impedance value. So this is the way to determine equivalent impedance when you have dependent sources present. Now I Norton is the short circuit current value at node A and B. By removing this load and doing a short circuit, that short circuit value is the Norton current source value. Coming to the solution, this is the circuit given, and then we know that the impedance offered by capacitance, which is XC equal to minus J by omega C, and that offered by the inductance is XL equal to omega into L, where omega is the operating frequency. So now we have drawn the impedance diagram where R is equal to 1, the XC equal to minus J by omega into 1 because C is 1 and C is 1 farad, so minus J by omega, and omega L, that is the inductive impedance, which is omega into 0.5. The inductive impedance is plus J. Now the equivalent impedance is determined across these two nodes by shorting the active voltage source that is independent with its internal impedance, that is short circuit, and then the resistance 1 ohm, and then this is J.5 omega, and this is minus J by omega BP dash, then Z equivalent equal to parallel combination of J.5 omega and 1 ohm, J.5 omega and 1, and then in series with J by omega. So multiplying numerator and denominator by 2, we get Z equivalent equal to omega with a J sign divided by 2 plus J omega minus J by omega. Z equivalent is determined by 2 plus J omega into J omega square minus 2J minus J square omega, where J square is minus 1, so this is plus omega minus 2J plus J omega square divided by omega into 2 plus J omega into 2 minus J omega, and then multiplying by 2 minus J omega, this coming out to be 2. Finding the imaginary part, which should be made 0 because it is told in the problem that the circuit should be purely resistive, that equivalent impedance should be purely resistive. To make the Z equivalent purely resistive, the imaginary term should be made 0. So the terms inside J should be made 0. It's minus 1, so minus 2 omega. And again this J square minus 1 minus minus plus. So this is like this. So only the J terms are this 2 omega square J minus J omega square, which gives omega square, and minus 4, which should be 0, omega equal to 2. So this is the answer. The value of omega in radians per second is 2. This is the answer. Thank you.